Okay, so I'll go over this paper we are presenting as a conference paper at NERPS 2025. It's about systematic reasoning. So the word on the street about uh, large reasoning models and other kinds of reasoning models like O3 and O4 is that they fail when they have to do multiple steps of reasoning. So they're good at doing the individual reasoning steps, but when they have to chain together multiple reasoning steps, they trip up. So in this work, we show that there are certain kinds of steps which are inherently more difficult, and all kinds of reasoning models fail when they are asked to perform only a few steps of this kind of reasoning. And these are reasoning steps that we as humans perform every day and are able to execute to solve tasks. So that's a primer of what this paper is about. Uh, and I hope I can discuss these ideas in these brief presentations, and you guys can judge for yourself the merits of this new idea about reasoning. I'll also give you an introduction about how reasoning tasks are set up and how models are evaluated on reasoning tasks. So that's something you guys can also glean from the presentation. Let's see, I think I'll have to break up the presentation into two videos, but that should be good. We should be good with it. So I'll begin by talking about what a systematic reasoning task is. So I'll explain in the context of the CLUTTR dataset, which is a dataset that tests systematic reasoning. But before I get to this CLUTTR dataset, let me give you a simpler example, which at least is memorable to me, and I think is a good point of introduction to a systematic reasoning task. So let's say you're trying to train a reasoning model to add two decimal numbers. And during training, you give labeled examples, so solved examples of adding two decimal numbers, but the two numbers being added are always less than 2000. So during training, the model is getting access to solved examples, but the numbers being added are less than 2000. Now, although you have this restriction in place, the model can in fact learn the rules of adding two decimal numbers. It can, for instance, learn how to take a carryover and then what to do with the carryover in the next step. And during training, if the reasoning model is able to learn these hidden rules of addition, then when you go to testing and you give it much bigger examples. So in testing, you ask it to add two numbers which are bigger than 50,000. The model should still be successfully able to do this because it knows the addition of adding two it knows the rules required to add two decimal numbers. And this is what a systematic reasoning task is. You're trained on small simple examples and you're asked to solve bigger, harder examples. But you should be able to do this if you, as a reasoner, are able to understand that there are some hidden rules that are being used to solve the small examples. And these hidden rules can help you generalize and solve these harder examples. So it's a kind of generalization task. And generalization is the heart of machine learning, in a sense. So let's get back to CLUTTR. Here the task is you're given stories. So you're given stories as story facts. So you're giving a set of story facts. And then there are some entailed facts, which are not explicitly given to you in the story. These entailed facts follow from the story facts because of some hidden world rules. And the reasoning model is given training examples where you get the story facts and the entailed facts, and the reasoning model should be able to learn the world rules, the hidden world rules from these labeled examples. And then during testing, it's asked to solve much harder stories in essence. So that's where systematic reasoning comes in. So let me go into these two examples. So these are two training examples in this CLUTTR dataset. So CLUTTR is a dataset that was released about 5 years ago, 2020-ish. And yeah, it's a very striking dataset. And it really showed why systematic reasoning is a difficult task. So here are two training instances in CLUTTR. The first one is this one. So there are two story facts. So the stories here are encoded as graphs, and the story facts are the black edges. So the black edges in the graph give you the story facts. So here there are two story facts. 5 is the sibling of 6 and 6 is the sibling of 7. And then there is this entailed fact that follows from the story, and the entailed fact is that 5 is the sibling of 7. And the hidden world rule that creates this entailment is that sibling of is a transitive property. This is a CLUTTR world rule. So here for this problem instance, the reasoning depth is 2. So you have to do one step of reasoning basically. You have to understand that sibling of is transitive, and that just solves the problem. So the reasoning depth is the distance between the source and the target node, the two nodes between which the entailed fact exists. So here the reasoning depth is 2, and the number of reasoning steps is 2 minus 1, which is 1. Here's a second training instance. So once more, the story facts are given as black edges. There are two story facts. 0 is the parent of 9, and 9 is the sibling of 8. The entailed fact is this dotted red edge, and the entailed fact is 0 is the parent of 8. The hidden CLUTTR world rule that creates this entailed fact is that if you combine parent of and sibling of, you get parent of. So these two relationships can be composed to give parent of. Basically, that's the hidden CLUTTR world rule. Once more, the reasoning depth is 2, so the number of reasoning steps you need is 1, and the reasoning depth is basically 2. That's the distance in this graph between this source node and this target node. The distance in the story graph between the source and the target node. And the source and the target node are the two nodes between which the entailed relationship exists. Okay, so your reasoning model sees these two training instances, and then it goes to the test environment. During the test environment, it's given this story. So 4 is the parent of 3, 3 is the parent of 2, and 2 is the parent of 1. And it is asked to find the entailed facts. So first thing I wanted you guys to observe is that this is a solution. So 4 is the parent of 1. To solve this, you need to do two steps of reasoning. So first you need to compose this parent of and sibling of. So that would imply that 4 is the parent of 2. And then again, So first you need to compose, sorry, this sibling of and sibling of. That would give you 3 is the sibling of 1 because sibling of is transitive. And then 4 is the parent of 3, 3 is the parent of 1. That gives you 4 is the parent of 1. So there are 2 steps of reasoning here required here. And the reasoning depth is 3. So if you notice the distance between 4 and 1, the 2 nodes between which this hidden entailed relationship exists, is 3 in this story graph. So this test instance is much more difficult than these 2 training instances. It requires 2 steps of reasoning, where these could each be solved with 1 step of reasoning. And that's where systematic reasoning comes in. During training, the reasoning model saw small examples, and during testing, it was asked to solve a more complicated example. And it should still be able to do it because the 2 world rules that it needs to solve this test instance are both apparent from these 2 training instances. So if it really learned world rules from the training instances, it would be able to apply them and solve this much more difficult test instance. And that's what CLUTTR is. It is a data set that requires systematic reasoning, and it's set up for these problems about completing stories or finding entailed facts from story facts. I'll stop here, and next time we will speak about some ways in which CLUTTR is simple, and the models that eventually would solve CLUTTR actually exploited this simplicity. And there are many real-world examples of reasoning that do not align with the simplistic structure of CLUTTR. So, yeah, hopefully we can complete our discussion in the next talk.